Hello everyone, I hope you're enjoying the conference. I've seen a lot of great talks and amazing speakers, really enjoying it. Unfortunately, I couldn't travel to Warsaw, but the organization was amazing and found a way for me to deliver my talk. Really appreciate it. Thank you all for joining my session, and let's talk a bit about Network Service Mesh. Before we get into the talk, let me introduce myself. My name is Ricardo Castro, and I'm the lead SRE at ANOVA. ANOVA is the global leader in remote monitoring of industrial assets. We provide industrial Internet of Things solutions that enable improvements for our customers in efficiency, safety, service, and profitability. We have more than 2,000 customers worldwide, we operate in more than 80 countries, and we monitor more than 1 million assets. And these numbers keep getting bigger and bigger. So, what will we be covering today? We will start by taking a look at the traditional service meshes. We're going to do a quick recap where we will refresh what problems it addresses and what are its main components. Afterwards, we'll take a look at where they fall short. We will see some of the use cases where they don't work or where the solutions they propose could be better. We will then move to talk about Network Service Mesh. We'll cover on a very high level what it is and what are some of its key concepts. We will then briefly take a look at some of the interesting NSM concepts that you should take a look after this talk. And before we go, I'll point you to some interesting resources where you can learn some more. So, let's start with complexity. Microservice architectures build applications as a collection of loosely coupled services. In this type of architecture, the goal is for services to be fine-grained and the protocols lightweight. The main objective is for teams to bring their services to life independent of other services. By building loosely coupled services, there's a reduction of the types of dependencies and the complexities around it. But that's easier said than done. Reliably managing network connectivity in distributed systems introduces its own set of challenges. Things like service discovery, load balancing, fault tolerance, distributed tracing, metrics collection, and security are just some of the concerns involved. How can a service mesh help us? A service mesh is the connective tissue between your services. It adds additional capabilities like traffic control, service discovery, load balancing, resilience, observability, security, and so on. A service mesh allows applications to offload these capabilities from application-level libraries and allows developers to focus on differentiating business logic. Typically, a service mesh has two main components, the data plane and the control plane. The service mesh data plane consists of business services alongside their sidecar proxies that are responsible for all the traffic. Control plane comprises a set of services providing administrative functions necessary to control the mesh. There are many service mesh implementations and they can help you in many ways. Here are just a few of them, and you might be using one of them already. You might be delivering awesome functionality by leveraging one of these solutions. So, where do they fall short? Service meshes work well within a runtime domain, but often workloads need to collaborate with services that live outside that runtime domain to provide their full functionality. But what are runtime domains and connectivity domains? A runtime domain is essentially a compute domain to run workloads. Traditionally, there's exactly one connectivity domain in a runtime domain, because connectivity domains are tightly coupled to runtime domains. What does this mean in practice? It means that only workloads in that runtime domain can be part of a connectivity domain, and each workload has only one option for connectivity domain. Like we've seen earlier, microservices is a popular cloud-native architecture, and it's all about loose coupling. To really take advantage of this approach, microservice components need to at least depend on each other. Application service meshes work well within a connectivity domain, and they target layer 7 payloads like HTTPS. They can help cloud-native workloads achieve this loose coupling through functionalities like service discovery and fault tolerance. But fully fledged services are seldom confined within a single runtime domain, and therefore a single connectivity domain. Services have to spawn across multiple connectivity domains to collaborate with each other. Let's now explore some of the use cases where traditional service meshes fall short, and we will then see how network service meshes can help mitigate those challenges. An example scenario is the multi-cloud hybrid cloud setup. In this scenario, you have several different and independent clusters which can be on a public cloud, private cloud, or on-premises. Workloads in each of these clusters need the ability to talk to each other. You could think of this scenario as an inter-cluster networking, but from the point of view of the workload. In short, we have workloads running on different runtimes and connectivity domains, and they need to talk to each other. Another example scenario is the Multi-Corp extranet. Here, workloads from different clusters need to collaborate with each other, independent of their connectivity domains. The major difference from the multi-cloud hybrid cloud setup that we just saw is that you now have different domains of administrative control. This means that you have different organizations managing their own runtime and connectivity domains. But yet, workloads inside each of these domains need to work with each other. Service mesh balkanization is yet another example where traditional layer 7 service meshes fall short. Traditional service meshes work well within a same cluster, and when local meshes need to collaborate, you usually link them through gateways. Typically, they are programmed with layer 7 static routes, which are both hard to scale and maintain. Traditional service meshes can't guarantee reliable networking here because they assume there's a reliable layer 3 under them. This is usually true inside one cluster, but cannot be guaranteed beyond that. The last scenario we're going to look at is the multi-service mesh. Typically, clusters can only support one service mesh. But in many circumstances, workloads need to interact with services that are running on other service meshes. Think, for example, about a workload in org1 cluster using Istio needing to communicate with a workload that lives inside org2 cluster that is using Linkerd. In this scenario and the previous scenarios that we've just seen, we saw those solutions are not optimal. It would be a lot easier if we could treat workload communication in a transparent way, independent of where the workloads are running. And this leads us to Network Service Mesh, or NSM for short. I'm lazy and Network Service Mesh is a bit long to keep saying it, so I'll keep repeating NSM as much as possible. So what is NSM? It's the hybrid multi-cloud IP service mesh that enables a few things. L3 Zero Trust, per network service connectivity, security and observability. Works with your existing CNI. Provides per workload granularity. Requires no change to your existing Kubernetes clusters and no change to your workloads whatsoever. NSM tackles these scenarios that we've seen previously in this talk by allowing individual workloads to connect securely independent of where they're running. Your runtime domain provides inter-cluster connectivity, and NSM doesn't require any change or interference in any way. And while it supports Kubernetes, it's not limited by it. Before we take a look at its key concepts, what are some of the examples where NSM can be useful? And these were taken from the documentation website. A common flat L3 domain that allows DBs running on multiple clusters, clouds, hybrid to communicate just with each other for DB replication. A single L7 service mesh, Istio, Linkerd, Console, Kuma, connecting workloads running on multiple clusters, clouds and on-prem. A single workload communicating to multiple L7 service meshes. Workloads from multiple companies connecting to a single collaborative service mesh from across company interactions. So essentially, these are concrete examples of the issues that we saw that traditional L7 service meshes can fall short on in terms of implementation. So let's now dive into its key concepts. And those are network services, network service clients, endpoints, and vWires. We'll then take a look at the NSM's API and at what are registries. So, in NSM, a network service is a collection of features that is applied to network traffic. These features provide connectivity, security, and observability. A network service client is a workload that requires a connection to a network service, and it does so by specifying the network service name. Clients are independently authenticated through SPIFE ID and must be authorized to connect to the requested network service. In addition to the network service name, a client can declare a set of key value pairs called labels. These labels can be used by the network service to select the proper endpoint, or they can be used by the endpoints themselves to influence how it will provide service to the client. An endpoint, also called a network service endpoint, is the entry point to the network service to the client. The network service is identified by its name and the payload that it carries, either IP or Ethernet, with IP being the default. Network services are registered with the Network Service Registry. So what can an endpoint be? It can be a pod running on the same Kubernetes cluster. It can be a pod running on a different Kubernetes cluster. It can be a VM. It can be an aspect of the physical network, or it can be anything else to which packets can be delivered for processing. What connects a client to an endpoint is also known as a virtual wire, or vWire for short. In short, a vWire acts like a virtual wire between a client and an endpoint. A client can request the same network service multiple times, and therefore multiple vWires connect a client and its requested endpoint. A vWire has a contract that establishes its rules, and those rules can be found in the NSM's documentation. Now let's take a quick look at the NSM API. It includes request, close, and monitor. A client can send a request gRPC call to NSM to create a vWire between a client and a network service. Conversely, to close a connection between a client and the network service, a client can send a close gRPC call to the NSM. A client can also send a monitor connection gRPC call to NSM to get updates on the status of a vWire that it has with a network service. Why would he do that? Because a vWire between a client and a network service always has a finite time to expire. The client may, and usually does, send new request messages to refresh that vWire. If a vWire exceeds its expiry time without being refreshed, the NSM cleans up the vWire. So, monitor connection calls allows a client to keep its vWires open. Let's turn our attention to registries. As with any other mesh, NSM has network service registries, in which network services and network service endpoints are registered. A network service endpoint provides one or more network services. It registers with a registry a list of network services by name that it provides and the destination labels that it's advertising for each network service. As we've seen previously, a network service is identified by its name and carries a payload that will either be IP or Ethernet. Optionally, the network service name may specify a list of matches. These matches allow matching the source labels a client sends with its request to the destination labels advertised by the endpoint when it registers as providing the network service. For example, if a client provided no source labels with its request for the service mesh network service, it will not match with service envoy proxy for the first match, and so will fall through to the final catch-all match with source selector and would be matched to the endpoint that advertised a network service named service mesh with the destination label of service envoy proxy. Now, if a client provided a source label of service envoy proxy, it would match with the first match and would be matched to the endpoint that advertised a network service named service mesh with destination label service VL3. Another interesting aspect is that NSM allows for multiple independently and mutually ignorant registry domains. The network service registry domain of a network service is indicated by suffixing an @domain to the network service name. In the example, we can see a network service named service mesh in the finance.example.com domain would be serviced by service-mesh@financeexample.com. Now, this was a lot. So, how does this all work together? So, a network service endpoint will register one or more network service with the NSM. It registers that list with the name and the destination labels that it's advertising for each network service. A client can send a request to the NSM to create a vWire between a client itself and the network service it needs. It can also close that connection, and because connections have an expiry time, a client can monitor that connection to keep its vWire open. The interesting part is that the NSM allows for workloads to request services independent of where they're running. It's up to the NSM to do all the necessary wiring, creating the required vWires and allowing communication between workloads in a secure way. Before we go, just a few more things. This talk explores what issues a network service mesh addresses and its key concepts, but there are more aspects that you can explore. You can take a look at interdomain, where a client may request a network service mesh from any network service registry domain independent of where it's running. You should also take a look at some advanced features. The NSM match process that selects the candidate endpoints for a certain network service can be used to implement a variety of advanced features, such as composition, selective composition, topologically aware endpoint selection, and topologically aware scale from 0. Also important to note is the fact that since 2019, the NSM has been a CNCF project and is currently in the sandbox maturity level. If you don't know what CNCF is, it's an open source software foundation that promotes the adoption of cloud-native computing. The CNCF is a subsidiary of the Linux Foundation and aims to establish a vendor-agnostic community of developers, end users, and service providers to collaborate on open source projects. CNCF projects are the foundation of Cloud Native. The CNCF provides support, oversight, and direction for fast-growing cloud-native projects, including Kubernetes, Envoy, and Prometheus. This means that the NSM is in very good company. I would also like to leave you with some links that you can explore to know more about NSM. If you want to try it out, follow the Run Network Service Mesh in Kubernetes tutorial. It features a full installation as well as several example use cases. My suggestion is to go through the key concepts again and then solidify them by trying out some of the examples. If you want another introduction to the NSM, follow the webinar Network Service Mesh and Introduction. It gives a very nice overview of the NSM. Also, check out the NSM roadmap to see what's on the horizon, and check networkservicemesh.io for the full documentation. So to recap, we started by going through an overview of traditional service meshes. We then looked at what are some of the use cases where they fall short. We then took a 10,000-foot view of the NSM and some of its key concepts. We explored several concepts like endpoints and network services, as well as the NSM's API, amongst other concepts. And last but not least, because we saw a lot of information in a short amount of time, we looked at some of the resources that will allow you to know more about the NSM. And that's all from my part. I hope this talk was informative for you. Feel free to ask questions or to reach out for me on my social networks. Thank you very much, have a great day and keep enjoying the conference.